lecture that was yesterday afternoon. Okay. Again, I'm sure you have questions. I mean, this is not entirely trivial material, so I'm sure some of you have questions, but you are feeling a little shy to ask. But if you ask, then you'll learn more. That's all. I mean, if there are some doubts, etc., that are not cleared at this point, then as we go along, those problems will remain unless those are clarified. So it's certainly almost essential that you get your questions answered, doubts cleared at the beginning. So yesterday I was discussing basically paramagnetism and diamagnetism, and the systems that I considered were all non-interacting systems. For paramagnetic, we were looking at a system of spins or magnetic moments which are localized on lattice sites, and then we looked at the response of that system to an external magnetic field. We got paramagnetic behavior, that the magnetization has the same sign as that of the external field, proportional to the external field, and from that one gets a susceptibility. And susceptibility, the important feature was this Curie law, that it's proportional to inverse of the absolute temperature. So that's first result, I mean simplest result. Then we looked at also paramagnetism of conduction electrons. That was a calculation that is called Pauli paramagnetism. And then at the end we looked at the ability of having diamagnetism of a system of electrons. But in all these cases, we basically looked at non-interacting systems. When we are looking at these localized moments sitting at lattice sites, we just looked at the energy of this system in an external magnetic field. There was nothing in the Hamiltonian that says that one of these moments interacts with another moment, which is of course not the case in reality. So one basically has to take into account interactions, and from today onwards, we'll be talking about what kind of interactions are there in a magnetic system, then what kind of effect those interactions have on the magnetic behavior. And there many interesting things happen. One has phase transitions, for example. One thing that everybody knows from the studies of this magnetostatics, for example, that there are ferromagnetic materials. There are materials which show a spontaneous magnetization, even when there is no external magnetic field. So that, I mean, the models that we have looked at, they don't answer how that happens. So first, I mean, in many other cases, there are many other different kinds of magnetic order that are possible: antiferromagnetism, then spiral order, there are spin density wave, all sorts of things like that. So that is the sort of most interesting part of studies of magnetism. That you first of all you have to figure out what kind of interactions are there among the magnetic moments that you are looking at, and depending on that, one can have various ordered phases at low temperatures, magnetically ordered phases, and what kind of magnetic order you can have, that will depend on what kind of interactions you have. So first of all, one is to understand what kind of interactions are there among these moments that are there in a particular system. So today I will start basically giving you some examples of such interactions. And then, I think in the second lecture onwards, we'll be talking about what effect those interactions have. And as I said, depending on what kind of interactions you have, you will have different kinds of ordered phases at low temperatures. So this ordering basically is an example of a phase transition. High temperature, there is no magnetic order. The system is basically paramagnetic. But as you go to lower temperatures, sometimes we'll see that below a certain temperature, some kind of order is developing. So that again is going to be the subject of my lectures. Maybe we'll start on it today, and then we'll continue in the next lecture, next day also. So, but today I want to give you some idea about what kind of interactions are there. So we are talking about interacting spin systems. And here again, as before, I use this word spin somewhat loosely. It doesn't mean that it's actually electron spin. That's the only thing that is contributing. There could be magnetic moment coming from orbital motion, etc. That we discussed last time. So the spin is something that just tells you about the magnetic moment. The magnetic moment is there. It can have different microscopic origins. But now, from today, we are going to concentrate on what kind of interactions are there among these magnetic moments. So, one of these interactions is something that Professor Barma talked about in his lecture yesterday. That was the exchange interaction. That is the most sort of common type of interaction that are there. And there would be something that looks like this. What notation that I'm using? So these magnetic moments are represented by these vectors. In general, we have to treat them as quantum mechanical objects, angular momentum operators. And it's a dot product, Si dot Sj. And I and J are sites on a lattice. We will be talking about basically crystalline materials for this, at least for the time being. So we'll be looking at solid with lattice sites. And ith lattice site, there is a magnetic moment Si. And so the interaction, this is different lattice sites. So basically, magnetic moments sitting at different lattice sites, they will interact. And there will be energy associated with this interaction. And this quantity that determines the energy is this quantity, which I call J, which is the exchange interaction. And it depends on how far these two lattice sites, I and J are. And typically, I mean, simple models, one just assumes that if I and J happen to be nearest neighbors, then there is an interaction. And if I and J are further apart, then there is no interaction. But I mean, at this point, we don't have to go into that. And this factor half basically takes into account the fact that, if you look at one pair I and J in this sum, it's counted twice. So that basically half factor takes care of that. And it's convention that you put a minus sign here. So what does it say? It says that if you put a minus sign there, if Si and Sj are parallel to each other, then the energy is the lowest, assuming that this J is positive. Right? If J is positive, and then these two are parallel to each other, that's the maximum value this can have. And then with a minus sign, that's the lowest value that the energy of that pair can have. And so if J is positive, then we call it a ferromagnetic interaction. And that basically says that positive J means that if two spins are parallel to each other, then that is the state that minimizes the energy of that pair. So the spins want to be parallel to each other at low temperatures. So specific forms of J, etc., that we'll to later on perhaps. As I said, the most simple situation is where you assume that this interaction is short range, and only I and J, when they're nearest neighbors, then the spins sitting at I and J interact with each other. And then there is just one constant, which is the nearest neighbor interaction, when Ri and Rj refer to nearest neighbor lattice sites. And then if the corresponding J exchange coupling is positive, then we call it ferromagnetic interaction, because that says that the energy will be minimized, lowered, if the spins are parallel to each other. And then you can see what would happen at low temperatures. I mean, this is something that we'll be getting into in much more detail later on. But it says that at low temperatures, then the spins want to be parallel. If the moments are on the average parallel to each other, then there will be a finite magnetization, because the spins at various different sites, they are all sort of on the average pointing in the same direction. And that may lead to what is known as a ferromagnetic state at low temperatures. right? So we can already see that, as soon as you put in this kind of an interaction, then this will have some effect on the state the spin system is going to be in at certain temperatures, and those phase transitions aspects, etc., will be coming to later on. Today, I want to spend maybe 5-10 minutes on why the interaction has this form and where does it come from? What is the physics of that? And Professor Barma had actually talked about it in the last lecture. But there were also some questions about under what conditions these moments are sitting on a lattice, under what conditions you should have to take into account the fact that there could be fermions, bosons, etc. So I'll just go through this very similar arguments, which will first of all tell you about the origin of this kind of interactions, also tell you about why, for example, when we are talking about paramagnets, these magnetic moments sitting at lattice sites, why I didn't worry about the fact that, these magnetic moments themselves, whether they're fermionic or bosonic, that we didn't worry about. So why was that? And I'll go through basically the same arguments as what Professor Barma was talking about, but slightly different context. This is what I'm going to do just now is known as Heitler-London theory of hydrogen molecule. So basically, you know that a hydrogen molecule is H2. So two hydrogen atoms, they come together, they form a molecule. Each hydrogen atom, of course, has a proton sitting at the center and an electron going around it. So I can consider the situation where these two hydrogen atoms are kind of far apart from each other. I have two different containers, and there is one hydrogen atom here and another hydrogen atom there. There is no issue of molecule formation. I mean, it's just the fact that there's two independent hydrogen atoms sitting there. But if I bring this, when they come close to each other, they bind to form a molecule, right? So the question is, how does one describe that process, and what kind of interactions are, in some sense, responsible for them to form a molecule? Yeah. So we just look at that in a very simplified manner, and this this is a little aside, so let me just use the other board, and here I am talking about the very theory which is known as of hydrogen molecule, H2. So the situation is like this. So there are these two protons. Each molecule has a proton and an electron which is going around. So this is plus E, and then there is an electron here somewhere. That's minus E. Similarly, here also there is a plus E here, proton. We'll be looking at only the electrons at this point. And again, minus E, another one. So now when these two are far apart, there is hardly any reason for this atom to consider that there is another atom sitting somewhere. So they are just independent hydrogen atoms. But when they come close to each other, they bind to form H2, hydrogen molecule. So we are looking at that situation where they're close enough so that the fact that you have two of them becomes important. Now, two of them basically means that there are two electrons. And whenever you have two electrons, they obey Pauli principle, etc., etc. So then the total wave function of the two electrons have to be antisymmetric. Right? This is what he was writing down, symmetric combination, antisymmetric combination. Now, this wave function will have two parts. One part is dealing with the positions, the orbital part of the wave function, another part dealing with the spin. So basically, you have to look at total wave function. Total wave function has to be antisymmetric under the exchange of all quantum numbers of the two. So if you have something that looks like some wave function which is spin part, space part, which is a function of the positions of these two electrons. And there is also a spin part which depends on the spin states of these two electrons. So this whole thing has to be antisymmetric. Under exchange. Exchange basically means that I look at, we call this electron, let's say 1. So that there is something called R1 sigma 1, and here have R2 sigma 2, other electron. Space part will be function of R1 and R2, and the spin part will be function of sigma 1 and sigma 2. And this product has to be antisymmetric. So what does it mean? That when I exchange all the quantum numbers, R1, R2 get exchanged, and also sigma 1, sigma 2 get exchanged. So the exchange of R1, R2 affects this space part, exchange of sigma 1, sigma 2 affects the spin part. Right? So this has to be antisymmetric. So if this is symmetric, this has to be antisymmetric, and this is antisymmetric, then this has to be symmetric. So this is something that is very important. There is a very basic that since electrons are fermions, the total wave function has to be antisymmetric under the exchange of all the quantum numbers. So if I exchange R1 and R2, then the space part can be either symmetric or antisymmetric. But if it is symmetric, then the spin part has to be antisymmetric. And similarly, if the space part is antisymmetric, then the spin part has to be symmetric. Yes.
Can this factorization into space and spin part always be done?
Not necessary. I mean, if you have basically the space part and spin part connected to something like, spin orbit kind of interactions, then this clean separation is not possible, perhaps. But in this theory, of course, nothing, one just doesn't look at anything like that. The interaction is basically the Coulomb interaction. That's the only interaction that is considered in this theory. The Coulomb interaction between this electron and that electron. So this is something which is very basic. So it says that the spin part actually affects what the space part of the wave function is going to be. If the spin part is symmetric, then this has to be antisymmetric, and if it is antisymmetric, this has to be symmetric. And the spin part, I am looking at two spin-and-a-half objects, right? So this comes back to what Mustan was talking about yesterday. Two spin-and-a-half, if we add the two spin-and-a-half, then you can get spin 0 or spin 1. Spin 0 is called the singlet, and spin 1 is called the triplet. So this is something that you have to just remember. Your spin part is symmetric if triplet, and this is antisymmetric okay. So if you are looking at the spin part which is corresponds to a triplet, then it is symmetric, and so then the space part has to be antisymmetric, and the other way around. Now, how does this affect the energy? So one then has to specify whether the spin part is symmetric or antisymmetric, whether it is singlet or triplet. We say that if it's a singlet, then the space part has to be symmetric. If it is a triplet, then the space part has to be antisymmetric. Now, how do you construct symmetric and antisymmetric space parts? That's the thing that, again, it was partly done by him. But I just write down space part now I'm looking at, and if I'm looking at some kind of a symmetric combination, space part is a function of R1 and R2. So, and one sort of, in the Hartley-Lardner theory, the space part is constructed from the ground state of an electron here, single electron, a single atom, or and I mean, one looks at this wave function. So just R1 something like that. So psi A R1 is the wave function when the wave function whose coordinate is R1 when it is here, and that is B. So here I'm putting R1 in A and R2 in B, and then we interchange R1 and R2. So R2 in A and R1 at B. So these are the two combinations that you get. And if you have a plus sign, then this is symmetric, right? If I want to construct an antisymmetric combination, then again I'll have the same thing, but we'll have a minus sign there. Understand? I mean, this is very basic actually. This sort of things you'll have to be sort of 100% sure about what is happening here. Then if I interchange R1 and R2, then this becomes that and this becomes that. So then there is a overall minus sign. Yeah. So we call that, let's say, some big psi symmetric, and you have a big psi which is antisymmetric. If I want to look at the energy, then I have to look at basically the expectation value of the Hamiltonian in this state or in that state. Yes? Hamiltonian of this is just the fact that there is a Coulomb interaction between these and these two, Coulomb interaction between these two, and also there is a Coulomb interaction between the two electrons. That's the Hamiltonian of the system. Depends on R1 and R2. So then I have some ES is some psi S. And similarly, E antisymmetric, where I have now, from here I know that if, for example, the spin part is symmetric, that the system is forming a triplet, then the space part has to be antisymmetric. So I can say that this EA basically corresponds to the situation where the spin part is a triplet, because that part is symmetric, and then the space part has to be antisymmetric. So I mean, I just making use of this Pauli principle, this EA, I can say that it is energy when the spins form a triplet. Similarly, when the spins form a singlet, then the spin part is antisymmetric, the space part has to be symmetric. So this energy we'll get when you have a singlet. Yeah. And since these two wave functions are different, these two will be different. That essentially means that the energy depends now on the spins. The spins, the symmetry of the spin part of the wave function, whether it's a singlet or triplet, that tells you about the symmetry of the spin part of the wave function. That in turn determines the symmetry of the space part of the wave function. And so, I mean, whenever you have a singlet here, then the space part has to be symmetric. Whenever you have a triplet there, the space part has to be antisymmetric. And these two are different. So the energy of the triplet state and the singlet state are going to be different. And that is that kind of interaction, S1 dot S2 kind of interaction that will give you different energies depending on whether the two spins are forming a singlet or a triplet. Yeah. So this is the origin of all exchange interactions. This is basically the reason that the electrons are fermions. So the function has to have some antisymmetry under exchange of all the quantum numbers of two of them. And then you get different energies depending on whether the spin part is forming a singlet or triplet. And the difference is reflected by saying that there is an interaction which is like S1 dot S2. Okay, so that is the basic origin. There is one side comment that I want to make. I mean, when we calculate this kind of expectation values, so on the left-hand side, you have again this combination and that combination. The right-hand side also, you have this combination and that combination. So there are two of them here. There is some Hamiltonian sitting in between, and two of them there. So there will be four terms, where you take the left one, this one on the left, and the similar one. Just let me write it down, so that. Where is it? So I'm erasing this. I mean, I assume that we don't need it at this point. So what I'm trying to do is I'm trying to calculate this quantity or that quantity, whatever. I mean, either the symmetric part or the antisymmetric part. So you have something that looks like this. Psi A R1 star and then there's some Hamiltonian that depends on R1, R2, also P1, P2, etc., etc. And then you have a similar thing on the right-hand side. So you can also have psi A. Same thing. There is this thing on the left, then there is Hamiltonian, and then there is this thing on the right. So I'm taking first term here on the left-hand side, and also the first term on the right-hand side. So this will be again psi A R1. This is, and then you have a double integral over R1 and R2, etc., etc. That's the expectation value of the energy, a term in the expectation value of the energy when you are using either symmetric or antisymmetric combination of these wave functions. These are the two things that you are using to calculate the expectation value. Right? So you have this is the direct term R1, R2, and on the right-hand side also you take R1 and R2, then you get that. So this term is fine, in the sense that, if I look at the R1 integration, you have psi A R1, also psi A R1 here. So there is no problem that, these two are the same functions. But if I now take this on the left-hand side and that on the right-hand side, then you will get something which is different. So this is the direct term. The exchange term that Mutsansi was talking about, again, let's call it psi A star R1, R2, again, your Hamiltonian, which has R1 and R2 in there. But now, instead of taking this, I am taking that. What is that? Then it is psi A R2, psi B R1. And again, double integral R1 and R2. Now you see that when I look at the R1, this is coming with A and that is coming with B. A is centered around the first proton, and B is centered around the second proton. And if these two things are far apart, then this R1, this and that will not have any overlap. So the situation again is like this. No? So you had an electron around this that I called psi A, and an electron around that I called psi B. If these two are far apart, a wave function which is centered at this point and the wave function centered around that point, they will not have any region where both of them are non-zero. Is it clear to everybody? So this exchange term, if I look at the support of this exchange term, It means that for this to be non-zero, both psi b and psi a have to be non-zero at some point. And if these two things are far apart, then they don't overlap. So there is no point in space where both wave functions are non-zero. And so then this integral will go to 0 if they are far apart. This is the situation that you have when you have two hydrogen atoms which are far apart from each other. There, one doesn't worry about the fact that you have electrons here, you have electrons there, and they have to be antisymmetrized and all sorts of things like that. So the symmetry property, of course, depends on whether you're looking at plus here and minus here. And the difference between these two comes from the fact that this integral gives you something which is different from that integral. But for the difference to be there, this kind of thing has to be non-zero. If this is 0, then it doesn't matter. Whether it's symmetrized or antisymmetrized, doesn't matter. Whether the particles are bosons or fermions, it doesn't matter. So basically, if I'm looking at two such orbitals which are very far apart from each other so that there is no overlap, then the statistics of whether you are talking about fermionic spin or a bosonic spin, etc., that doesn't matter. Whereas here, if they are close to each other, that's when they form a molecule. That's a situation where the spacing between these two nuclei or protons, whatever you want to call it, is small, so that this quantity, psi A and psi B, will have overlap, so that there are some regions where both of them are non-zero. And so this integral, which is the exchange integral, will not be 0. And so then, of course, I mean, the singlet triplet difference, which gives you this J over there, that will be there. So basically, then this comes from the fact, this J comes from the fact that there is a difference between the energies of the, basically whether the spin part forms a singlet or a spin part forms a triplet, so that determines the space part, and that in turn determines what the energy is going to be. But this difference is there only when the wave function here and the wave function there, they have some region where both of them are non-zero. So when you have localized spin at one lattice site, localized spin at some other lattice site, localized basically means that their wave functions don't have overlap. So then one doesn't have to worry about whether the spins are coming from fermionic ion or bosonic ion. And one doesn't have to take into account Fermi statistics, Bose statistics, all those things become irrelevant. Whereas if close to each other, that is the situation that you have they come close enough from a molecule. Then, of course, singlet and the triplet will have different energies. And from that, one can calculate the energy of the binding energy of the hydrogen molecule, et cetera, et cetera. But those I'm not going into. The two things that are important is that the symmetry of the spin part determines the symmetry of the space part, and then that gives you a difference between the singlet and the triplet energy. That, in turn, can be written as an exchange interaction, which is form S1 dot S2. And we have to quote that only when these two things are close to each other, so that their wave functions, two wave functions, psi A and psi B, they have a region where both of them are non-zero. Okay, so is there any, I will not come to this part later on, because now what we'll be trying to do is to try to understand what kind of behavior one expects when these interactions are there. So it's good to understand what is going on here. Yeah? So this model is known as Heisenberg model. The exchange mechanism that I told you about is basically a Heisenberg exchange mechanism. This is called the Heisenberg model. And typically, I will look at only situations where this interaction is short range. And you see, short range basically means that again, just coming from here, this interaction will be there only when there is some overlap between the wave functions. Now, if I look at two spins which are far apart, then these wave functions will not have much overlap. So basically, then the interaction will go to 0. And so this function typically is a short-range function. It's a non-zero only when the distance between this I site and j site is the smallest possible value. Smallest possible value basically corresponds to them being nearest neighbors. So then this then becomes, I mean, if you just have only nearest neighbor interaction, so this can be written as sum over minus times j nearest neighbor pairs So j is the value of this exchange integral when I and j are nearest neighbors on the lattice, and we are assuming that whenever I and j are next nearest neighbors or more distance pairs, then the corresponding exchange integral goes to 0, and so there is no no interaction. So this is typically the kind of Hamiltonian that I'll be looking at. Only nearest neighbor interactions, and then there is a si dot sj interaction, which is the exchange interaction coming from this kind of a mechanism. And then it becomes important what sign this j is going to have. J is basically the difference between the singlet and the triplet energy. So, and the calculation of these things involves integrals that I have just written down over there. So that will depend on the wave functions and so on and so forth. So if j is positive, this model is called a ferromagnetic model. And the reason is quite obvious, that if j is positive, the energy is lowered when these two spins are parallel to each other. When I say parallel to each other, that of course is classical language. We are treating them as vectors, and they can be pointing any direction and so on. In quantum mechanics, that basically means parallel basically means that they form a triplet. So all of you know that what is the wave function associated with the singlet and the triplet. This was discussed in detail in the last lecture. So parallel basically means the triplet state has the lower energy when j is positive. And if j is negative, then we have another kind of interaction which leads to a different kind of order. It's often called anti Justia.
So, sir, if there are two sites, like for a hydrogen atom, then we have spins, and in that case, the singlet and triplet I can understand. But what if we have like a lattice, like you have written over here,
Yes.
and I plus one side? The nearest neighbor sites are what is where the interaction is actually focused.
Yes.
So these interactions individually they form triplets. Or for a ferromagnet, the ground state is triplet.
Yes.
But what does it mean, like for
the
an
whole thing,
entire
yeah.
lattice to be?
No, it's a very good question. So I mean, then we have to consider. You see, when you look at two, to minimize the energy, they have to be in the space. They have to be s equals 1 state. That's what a triplet. So I mean, if three spins, then you can have the maximum spin that you can have. So you add 2 spin a half, that will give you 1 0. Add another half, that will give you 3 halves and half. So it's the 3 half state, the maximum total spin state, that will have the lower energy. Yeah. Whereas for an antiferromagnet, it becomes much more difficult, because then the singlet state will have for two singlet state has to be the lower energy. The question is then, you can combine all the spins to get some spin 0 or not. So that state then will have, because n spin a half combine the angular momentum, there also you can get total spin equal to 0. So that will be preferred in an antiferromagnet. So this is the basic Hamiltonian that we'll be dealing with when we talk about interacting spins and the kind of order that can emerge from these interactions. Of course, I mean, this is a simplification because, as somebody pointed out, we are just looking at two such electrons in vacuum, so to speak. And then, I mean, when we're talking about this, we just look at this hydrogen atom, that hydrogen atom, both of them are in vacuum, and whether they are close to each other or far apart from each other, that is what one is looking at. But in a solid, of course, it's not a situation like that. Solid, these spins are sitting in an environment where there are all the other particles are there, right? So you cannot treat that as a vacuum. And the important thing is that crystalline solid has some symmetry. That, you know, simplest thing is a cubic lattice, then you can have different kinds of lattice and so on and so forth. So if I now look at, for example, a particular spin here, and I can draw only in 2 dimensions, so I'll draw a simplest lattice, which is a square lattice. So if I look at this, let's say we call this S1. And if you call this S2, then there will be S1 dot S2 interaction, S1 dot S3, etc., etc. Those interactions all will be there. But the important thing is that if I look at this spin S1, it knows that there is another atom here, another ion here, another ion here, another ion there. And the question is how these ions are going to modify this Hamiltonian. Here we are just looking at this pair. We are not looking at the fact that, you know, you have this other. These are also nearest neighbors. So this distance between these two are small. This distance between these two are small, etc. So the presence of all these other ions on the lattice is going to affect what happens here. And this environment is not rotationally invariant. Environment is basically has discrete symmetry, right? If I want to look at the symmetry operation of this square lattice, if I want to look at rotation, then it can rotate only by 90 degrees or 180 degrees, etc., to come back to the same lattice. So it has a symmetry that is governed by the symmetry of the crystal that we are looking at. And so whereas this interaction is rotationally invariant in spin space, right? It's a dot product of 2 vectors. If I rotate both the vectors by the same amount, dot product doesn't change. So this has rotational invariance. S1 dot S2 interaction has but in spin space, I'm rotating the spin vectors. And here, in a crystal, the environment is not rotationally invariant. But this I am talking about in coordinate space. Coordinate space basically is the space in which the crystal is sitting. So if there is something that sort of connects the coordinate space to the spin space, then the effect of this will be felt there. So that is the point, that when the spins are sitting in a crystal, it is not always clear that you will have this rotational invariance in spin space, because there are terms in the Hamiltonian that one thing that is quite clear is that if you have some L dot S interaction, spin orbit interaction, orbit is taking place in the coordinate space and the spin is in the spin space. But if there is an interaction between these two, then the asymmetry that you have in the crystalline environment, that gets also reflected in this kind of interactions. So there are things like, you know, crystal field and spin orbit interactions that again Professor Barma talked about. mentioned in his lecture. So those things are there whenever you are looking at spins which are sitting on a lattice. And so this form, which looks quite simple and nice, is sort of an idealization. Typically, there could be asymmetries in this interaction. Could be asymmetry in the coordinate space, asymmetry in the spin space that show up, and the Hamiltonian then looks somewhat different. So, and in real systems, one has to sort of be somewhat careful about writing down, what is the appropriate Hamiltonian for the system that we are looking at, whether this simple Heisenberg exchange is a good description or there are strong asymmetries. Depends on how the two spaces are coupled to each other. So what I'm going to do is I'm going to write down some Hamiltonians in which one has asymmetry coming from the fact that the spins are sitting actually in an environment which is not rotationally invariant, which then couples to the spin space and makes the interactions also not rotationally invariant. So again, one has to do detailed calculation to take into account these effects of the lattice, which is beyond the, actually I don't know how exactly one does those calculations, but I can tell you a little bit about what effect it has on the spin-spin interactions that we are starting with the Heisenberg interaction, which is sort of invariant under rotation in spin space, and how that gets modified. So this is the simplest Hamiltonian. Then we look at anisotropies. Which sort of takes one away from the fact that now you have broken rotational invariant, and there are many different kinds of anisotropies that one has to look at. One is what is known as single ion anisotropy. Basically means that doesn't even show up in the interactions. It shows up in a single ion term, just involves single spins, but it says that there are some special directions along which the spin would like to point. So there could be a term that looks like some constant A, sum over I, S I Z squared. This is quadratic anisotropy, which basically says that, see here, of course, the interaction term is rotational invariant. If you look at a single spin term, there is nothing that says x-axis, y-axis, and z-axis is preferred. If you don't have a term like that. If we have a term like that, then depending on the sign of A, the spins may want to orient in the z direction or want to orient away from the z direction. Is that clear? So A is, let's say if I have A bigger than 0, then basically means that you have to have SIZ, roughly speaking, small, and A less than 0, you want to have SIZ large. Again, these words are being used loosely. We are assuming as these words make sense when this S is just a classical vector, but now this is a quantized thing. So SIZ can have discrete values. So when I say SIZ small, that basically means that it has integer values. So smallest integer value that it can have. Depends on the S. If S is half, then it can have plus half minus a half. Then it doesn't matter because it's a square of that. But if, for example, S is equal to 1, then it can have plus 1, 0, minus 1. And then the question is whether the 0 state will be favored or the 1 state will be favored. So that depends on the sign of A. And this is quite common, and this anisotropy, because of its nature, it wants to say whether the z direction is favored or whether z direction is not favored, is called, so A less than 0 means that it SIZ wants to be large, and this is called easy axis. And when SIZ is small, that means that the projection likes to be in the xy plane, and so this is called easy. So depending on the sign of A, this, the spin wants to point one direction, or it wants to maximize its projection in that direction. That is the easy axis anisotropy. And in some other cases, depending on, again, sign of A is negative, then A is negative basically means that it's easy axis, and A bigger than 0 means it's easy plane. And then you see that we cannot treat the problem as basically rotationally invariant in spin space. This term breaks the rotational invariance. And particularly if you have basically something that tells you about behavior near phase transitions, critical phenomena, there the symmetry matters very much. And so whether you have easy axis anisotropy or easy plane anisotropy, that can totally change the behavior of the system point where it is going from some paramagnetic state to ferromagnetic state or something like that, near phase transitions. So this is called single line anisotropy. This is called uniaxial anisotropy. Uniaxial basically means that some axis has been chosen, which is the z axis in this particular case, that energy, whether the projection in that direction is large or small, that makes a difference in the energy, or just energy of one spin. We are not even talking about interactions. And then there could be interactions that on top of that. So the Hamiltonian will have a term that looks like this, maybe, or this also becomes anisotropic, which I'll come to in a minute. But in the Hamiltonian, there will be additional term that looks like this, which says that the z component of the spin wants to get maximized or minimized. There is another kind of symmetry that is quite common, which is called cubic anisotropy. And this term has a form which sort of looks like this, some constant b, and then SIX to the power 4 and it's cubic anisotropy because, you know, I mean, you know, it's sort of like symmetry of a cube in the sense that, you know, this each component is coming with the same 4th power. And now I will actually not tell you very much about what happens here, because if I now want to minimize this quantity, then that depends on, or maximize this quantity, that depends on, I mean, whether you want to minimize this quantity or maximize this quantity, that depends on the sign of B. B is positive, then you want to minimize this quantity, and negative B, you want to maximize this quantity. So which directions in the spin space will minimize or maximize the energy? That is something that you have to work out. I think there is a tutorial today, and one of the questions deals with that, that if you have a term like this, and what one is there, I mean, easier calculation is to assume that this S is just a classical vector, fixed length. So you see that if, for example, you have this term, and x, y, and z, these are just the components of a classical vector in the x, y, and z directions. Then, for different orientations of this vector, this term will have different values. Is that clear to everybody? that if I have, let's say it's pointing in the x direction, then this y component is 0, z component is this 2 are 0, this is equal to 1. But if it is pointing somewhere in between, then it will not be 1, it will be something else. So you have to figure out whether going away from the axis, whether the term that we have there is increasing or decreasing. And you have to find out basically which orientations will maximize this quantity, which orientations will minimize this quantity. And that is important because that will determine, depending on the sign of B, what are the preferred orientations of this particular spin vector. So that I will not, but you know, it certainly says that all directions in the spin space are not equivalent. If we had just s squared or something that is, let's say, instead of 4th power you have squared, then of course this is essentially s squared. And it doesn't depend on which direction it is. Right? So if you have here square, 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 then that's the square of the vector. And that vector, that eigenvalue of that in quantum mechanics is just s times s plus 1. Doesn't matter whether what the z component is going to be. But now that symmetry is broken. Things depend on which direction, so to speak, the spin is pointing. And depending on the sign of B, one has to figure out what are the preferred orientations. And that breaks the isotropy in spin space. So that's why typically, of course, it says these are all anisotropies. So something that breaks the isotropy in spin space, some term in the Hamiltonian, they will count as anisotropy. And it is single ion anisotropy because involves only one spin, some SI. Is that clear in the sense that how this term is breaking the isotropy in spin space and what are the preferred orientations and things like that? Those are important because in real systems, this kind of anisotropies are always there. And so there you have to figure out what kind of orientations the spins in your system would like to have. So I go till 11, half an hour more. Okay, that gives me enough time. So this is one kind of a crystalline environment which is not isotropic and which then makes the spin space also. There are terms which are not isotropic in spin space that come into the Hamiltonian. It's a single ion. So now I go to the other board. So this kind of anisotropic environment also can make anisotropies in this kind of a term. This kind of term is calling the exchange term, right? So the anisotropy, what I'm looking at here, is referring to just a particular spin. But there could be also what I call exchange anisotropies. See, what this particular form says that your Hamiltonian has this form. H is some minus j, and then sum over nearest neighbors, SIX, SJX, so this is isotropic, is invariant under rotation. Same J is coming from, is telling you the interaction between the X components, Y components, and Z components, right? This is what makes it S1 dot S2, and the whole thing is invariant under global rotation in the spin space. But now we are saying that this isotropic can be broken. So I can in general have some form which says that the interaction between the X components is different from the interaction between the Y components and the same. So I mean, so I can in principle put in keep the global minus sign, and we'll Jx here, Jy here, Jz here, and sum over nearest neighbor pairs, let's say, for simplicity. Again, looking at the interaction between Si and Sj, but the interaction between the X components is given by this number, Jx, Y component is given by Jy, and Z component given by Jz. And these terms need not be all the same. So then, of course, it is no longer isotropic. And it depends on, depends on the values. Jx, Jy, and Jz says that, what they want to do, what configuration of S1 and S2 or Si and Sj is going to minimize this term. Earlier case, we had just this. It said that S1 and S2, when they're parallel to each other, then the energy is minimized. But here, it's not like that anymore, because it's no longer isotropic. And in particular, there are special I want to talk about here. We'll call it, let's say, J1. This also I call J1. And this I call J2. The interaction between the Z components is J2, and the interaction between X and Y components are both equal to J1. Now, you can see that the important thing is that whether J1 is bigger than J2 or J2 is bigger than J1. Right? If, for example, there is an overall minus sign here. If, for example, J2 is bigger than J1, then if the spins lie in the Z direction, you will get an energy which is minus J2, and if they are in the XY plane, then you will get energy which is equal to J1. So J1 bigger than J2, then it is energetically favorable for the spins to lie in the Z direction. And similarly, the other way around. So there, if I want to sort of find out what relative or what are the orientations of this S1 and S2, which will minimize this, then this is called again spins preferred to point in Z direction. Again, this is sort of similar to this easy axis. So easy axis coming from single spin anisotropy, which said that if A is negative, then you have easy axis anisotropy, so the individual spins want to point in the Z direction to minimize the energy. But here, if this interaction is bigger than the other two, then again, it's coming from this pair term, not from the single spin term. But then again, you say that the spins prefer to point in the Z direction. Other way around, if J2 is less than J1, the spins prefer to point in the XY plane. If this term is big, then if they're in the XY plane, then we'll get a large negative term coming from the coming from this, and This should be clear. That depending on the value of the exchange interaction coming in the x direction and y direction and z direction, the spins may prefer to point either in the xy plane or the third direction, z direction. So again, this has broken the isotropy in spin space in a particular way, and some directions in spin space get preferred, either the z direction or the xy plane, and there are some extremes of this kind of anisotropy which are also important, which will now, many of the models that we'll be looking at will be somewhat like that. So if I now put this, take this case, and I put J1 is equal to 0. So there is no interaction between the xy components. Then the Hamiltonian becomes minus sum over nearest neighbor pairs, sum J2 only the z components are interacting. Energy is given by only the z components of the two spins S1 and S2. And this kind of a model typically is called the Ising model, in the sense that, now we have just numbers here. This actually becomes a classical model because the Hamiltonian involves this z components only. The z component of a particular spin, depending on what the value of S is, can take this 2s plus 1 values, going from minus s to plus s. So these are just numbers. The z component of different spins also, of course, commute with each other. The quantum nature of the Heisenberg model comes from the fact that when I'm writing this, it involves both x, y, and z components, and these components don't commute with each other. Whereas if you have just the z component, then other components are not appearing in the Hamiltonian. So then that becomes a classical thing. I mean, it's just some numbers. So this model is studied very often in statistical mechanics. In particular, this model, when this S is equal to half. If I look at half integer S equals to half, then Sz can have plus half or minus half. So then one writes this as, this then becomes sum over nearest neighbors, some interaction j, and sigma I, sigma j, where this sigma I plus 1 or minus 1. At this half I am absorbing in this J2 and then defining some j here. So basically, typically a minus sign there. We are dealing with this variable sitting on a lattice which can take only two values, plus 1 or minus 1. And the interaction is just sigma I, sigma j with some coupling constant there. And if j is positive, then sigma I and sigma j, they want to have the same sign, which basically leads to ferromagnetism at low temperatures. If sigma j is negative, the whole thing is positive, then sigma I and sigma j want to be opposite to each other. That leads to what is known as antiferromagnetism. So this is one of the simplest models of statistical physics, and this is very important model because some exact results are available on this. Many of the other models, no exact result is available, so one can get pretty good idea about what happens in this model by various approximation methods or numerical methods and things like that. But this Ising model in 2 dimensions in particular has been exactly. So very important results available for the Ising model, and this is in later lectures I will often talk about only the Ising model. This is the simplest one. The other limit, when I put this J2 equal to 0, then again your Hamiltonian has SIX, SJX, and SIY, SJY. Only the x and y components of the spin are important. And then this is called the XY model. Two-component spin, x component and y component. And that also is a very important model in statistical physics in general. In magnetism, it just comes from this kind of anisotropy, exchange anisotropy. And if one of them if the ZZ interaction is 0, then of course you have this only XY component interactions, and then you can treat these spins as two component spins, only the X and Y components are important. And one has this model which is called the XY model, which important magnetism, but it also is important because there are many other physical systems which are very different, for which also the description can be formulated in terms of this XY model. I mean, you may have heard about superfluidity, helium. In helium, there is a superfluid phase. Of course, when you know about superconductivity, there is a normal phase, and then lower temperature system becomes superconducting. And the phase transitions, if I want to study this normal to superfluid transition or normal to superconducting transition, then they actually can be formulated in terms of this XY model coming from the symmetry of the order parameter, which is again something that if time permits, I'll talk about in perhaps the last lecture that I have. But all these models are important in magnetism because it's a material property, in the sense that which one of this coupling constant is bigger, etc., etc. That depends on which material you are looking at. So you can have realization of Ising model or XY model even in magnetic systems. Okay, so of course, I mean, this is just the beginning of the tip of the iceberg, so to speak. That you can already see that many different kinds of models you may have to consider depending on the particular physical system that you want to study. I'll just give you some more examples of models like that, which also come up in the context of studies of magnetism. So we've talked about Heisenberg model and different anisotropic versions of that, single ion anisotropy and also exchange anisotropy. But the interaction is, Heisenberg model interaction is the simplest one. S1 dot S2, and that's theoretically most of the calculations that I'll be doing at least will be assuming that particular form or the Ising model, which is the classical model, much easier to handle. So what other kinds of interactions might be important? Of course, I mean, there is one interaction that is always there, which I have not written down, which is basically the dipolar interaction. So you have magnetic dipoles. Spins are basically magnetic dipoles, dipole moments. So you know that two dipoles interact with each other in a particular way. So that interaction is always there in all systems, but in most cases, I mean, when you have interactions of this kind, that dipolar interaction is much smaller in magnitude. So one doesn't have to worry about it, but it becomes important when you have in the ferromagnetic state, you have these domains forming and things like that. There the dipolar interaction becomes much more important. But even in this microscopic interaction, there could be many other forms. For example, there is this name, Zyloshinsky. Moria interaction. And this has a peculiar form. This has a S1 cross S2, then dot product some R12. And then there are some factors of R downstairs. I don't remember how it depends on the distance. But the point is, this is, of course, not this explicitly anisotropic. I mean, this, first of all, relates to how this R12 is the vector from 1 to 2. So if you look at two pairs, then the interaction, of course, will depend on how these two pairs, not two pairs, two spins, a pair of spins. Interaction depends on how they're located to each other in space, because that changes this R12. vector. So, and this comes from spin orbit coupling and so on and so forth. So, but it's a very complicated form of interaction, but this is often present in actual systems. So, one has to sometimes worry about the effects of this Zalewski-Moria interaction. There is something which is called Ruderman-Kittel Kasuya I'm not sure about the spelling here. It's called RKKY interaction. And this is relevant to the system that Mustansir was talking about. If you have two magnetic impurities in a metallic system, so let's say some small percentage of iron in gold. The gold by itself, of course, is a metal, so there are conduction electrons. And this iron, if you have a small number of iron impurities there, they form local moments. And these local moments interact with this RKKY interaction, which is of the form S1.S2. But there is a but this is funny dependence, that it depends on R12, but it depends in an oscillatory manner. Kf is the Fermi wave number of the host metal, which some value is there. So, and then if I look at two spins at S1 and S2, interaction depends on the distance. Distance, it falls off as q power of the distance, but more importantly, it has this oscillatory form. So, some distances interaction can be ferromagnetic, some other distances interaction can be antiferromagnetic. So, again, this is there, and this leads to what is known as spin glass kind of behavior, disordered magnetic system. Again, a very important area of research, but of course, it will be difficult to go into details of that at this point. So, in a solid, things are quite complex because of all these things. That the fact that you are no longer in an environment which is rotationally invariant, which is not isotropic. Solid, of course, crystalline solid is not isotropic. So that leads to various kinds of anisotropy. There are many other effects that are there coming from, in this case, Zalewski-Moria becomes important when you have strong spin orbit coupling. RKKY is a special case where you have magnetic impurities in a host metal. The magnetic impurities have magnetic moments, and how these moments interact with each other, that has this funny dependence on the distance between the 2 points. There are many other kinds of interactions. There is super exchange, indirect exchange, all sorts of things are there. I mean, if you have then something like what is known as Hubbard model, and if you begin to take into account the effects of correlations, effects of interactions between electrons, then you can have something, antiferromagnetic interactions coming from that strong correlations, etc., etc. So basically, don't want to go into too many other details, but just wanted to give you some idea about when you want to worry about the effects of interactions among the spin moments, you have to know, of course, what the interaction is, and there is a very wide variety of interactions that are realized in solid-state systems, depending on which material you are talking about. And theoretical studies of all of those things is important, because since these are realized in experiments, to understand what is going on in experiments, one has to then study the corresponding model. But it's not always easy to figure out which model is relevant to which experimental system. One has to do a lot of experiments, look at many different properties to find out how to write down the Hamiltonian for that system, which terms are important, which terms are not important, and so on and so forth. So I guess afternoon. And there I'll start to develop the methodology that one uses to theoretically study the effect of these interactions. So yesterday we just talking about no interactions, just a spin in a magnetic field. And there again we saw that there are many different kinds of possibilities. But now I'm talking about interactions, as I just pointed out here, many different kinds of interactions are there. So the question is then how these interactions affect the physical properties of the system. And again, the most important thing is that these interactions may lead to interesting phases, which are not paramagnetic or diamagnetic, can be ferromagnetic, antiferromagnetic, spin glass, all sorts of magnetic phases, magnetically ordered phases are possible, and study of that is going to be the subject of what I'm going to do in the next few lectures. Okay, so we'll stop here.